Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open. This hour is your hour. Okay, let's move on and take the first listener phone call.
Hi, this is Armand from Queens, New York, and I listen to you on YouTube. I watch these murder mysteries, and they usually give the suspect a polygraph. But I've heard that polygraphs aren't that accurate. So what are your speculations on that? And do you think there's new technology, coming that can be more effective than the polygraph, like brain scan or something like that? Thank you very much, and have a great day.
Well, yes, ever since ancient times, people have wondered, how do you detect if someone is lying to you? During the Middle Ages, for example. During the Middle Ages, somebody would grab both wrists and check your pulse in your wrist, and then ask you questions. If you begin to hesitate, act nervous, and sweat, you could detect that because your pulse rate went up because somebody was holding both wrists as you were being interrogated. So that was crude, but it was a way in which you could detect increase in blood pressure, which does correspond to lying in certain circumstances. Today, we have a battery of ways in which we can so-called detect lies. We can look at, for example, sweat. Sweat is salt water. Salt water conducts electricity. So by analyzing the conductivity of your skin by putting two small electrodes on your skin, you can detect whether or not you're sweating and therefore whether or not you are, quote, telling a lie. Your breathing rate, your heartbeat, the conductivity of your skin, any number of ways are put together to create a polygraph which can be beaten. If you can psychologically control your body so that you don't tense up, you don't start to sweat, get nervous, but you distract yourself by thinking about the seashore or birds or thinking about something else, you can actually train yourself to defeat a polygraph. And now we have brain scans. Get a copy of my book, The Future of the Mind, and you'll be shocked to find out how much materials that we can actually get from the living brain. By looking at blood flow in the brain, we can actually see thoughts as they're being created in the living brain. This is amazing. This means that old wives' tales can actually be proven to be correct in some cases. Many parents believe, for example, that teenagers suffer from brain damage. Well, that's partly true. Brain scans of the prefrontal cortex of teenagers show that it's not fully developed. So their ability to evaluate risk-taking is faulty. And that's why teenagers take unnecessary risks. Another old wives' tale that you can show by using brain scans, well, many people believe that when a man talks to a pretty girl, he starts to act stupid. Well, if you brain scan someone who's talking to a pretty girl, sure enough, blood drains from the prefrontal cortex, and the man starts to stutter and act mentally retarded. So this is actually a biological mechanism that you can measure, quantify, something that most people believe, and that when a man talks to a pretty girl, he starts to act stupid. Well, can you use this as a lie detector? That's the question, and we'll answer that question after the break. Welcome back to Science Fantastic with Professor Michio Kaku. I've written 4 New York Times bestsellers, and one of them is The Future of the Mind, where I do talk about brain scans, using brain scans as a lie detector test. And the question is, how accurate are they anyway? Well, it turns out that when you look at brain scans of the human brain, when you tell a lie, it registers the usual thing. The brain, of course, controls sweating activity, involuntarily sweating activity, pulse rate. You can pick that up on a brain scan. But lying and telling the truth or telling a lie, we have not found the center in the brain that does that. Maybe there is no center of the brain that does that. We don't know. But at the present time, we have not located that point of the brain where, if you tell a lie, it begins to light up. So when people say that with 99% accuracy, brain scans can detect liars, well, that's kind of stretching it. Brain scans can detect a lot of things, which you can also detect using ordinary polygraphs. But brain scans are still primitive. We're in the beginning stages. Maybe eventually we'll find that center of the brain that regulates truth and untruth. But right now we have not yet found it. So don't believe it when people say that with 99% accuracy we can use MRI scans as lie detectors. That's not to say that it won't be possible in the future, but at the present time, brain scans are still in their infancy. Okay, well, let's move on to the next listener phone call.
My name is Abigail, and my question is, why do planets with larger mass have a different amount of gravity than planets with smaller mass? Thank you. I'll listen to the answer on.
Well, it was Isaac Newton himself who figured out that the larger the planet, the more the gravity. In fact, he found the precise relationship between gravity and mass. The force between two objects is proportional to the masses of these objects divided by the distance squared times a constant, the universal gravitational constant. Using that equation, bingo, he was able to calculate the motion of comets, like Halley's Comet. That was a tremendous victory for science, because people didn't know what guided the planets, and especially they didn't know where comets came from. But using Newton's laws, you could actually calculate the trajectory, the future trajectory of Halley's Comet, and then Halley was able to predict when Halley's Comet would return back to light up the skies over London. But you ask a slightly deeper question. Why? Why is it that gravity is related to mass? Well, now we have yet another theory, Einstein's theory, that takes it one step farther. And that is that mass warps the space around it. The bigger the mass, the more the warping. The more the warping, the more the distortion of an object moving in the gravitational field. So objects move in a curved line going around the sun, like the Earth, because the sun has warped the space around the Earth. And that's why the Earth goes around the sun. In fact, that's why you're sitting in your chair right now. How come you're not floating? How come you're not being hurled 1,000 miles per hour into outer space? Because that's the velocity that you are traveling at right now. You are traveling at 1,000 miles per hour. The Earth's circumference is 24,000 miles. And there are 24 hours in a day. So bingo, you divide and you get the fact that you're moving at 1,000 miles per hour. So why? Not because gravity is pulling you down, that's what Newton would say, but because space is pushing you down. So to summarize Einstein's theory of general relativity in one sentence, it is that gravity does not pull, space pushes. And then you may ask yet another question. Why is that? Why is that? Why is it that the larger the mass, the greater the warping, and the greater the gravitational attraction? Well, the answer to that is we don't know. Sorry about that. That is a postulate given to us by Newton and now by Einstein. Where does that come from? We think that eventually comes from string theory. But then you may ask another embarrassing question. Where does string theory come from? Well, at that point, I plead guilty. I don't know. And for that matter, neither does any physicist on the planet Earth. Okay, well, let's move on now to take the next listener phone call.
Hey, this is Dave P., 1340 KPRK, Livingston, Montana. My question to you is, what is your opinion on wormholes? Do you think that it's something that someday we can exploit and actually use? Do they exist? And please give me your opinion. Thank you.
Well, if you want to see a wormhole in graphic detail, look at Star Trek Deep Space Nine. Whenever Star Trek Deep Space Nine begins, it opens up with a wormhole that looks very much like a whirlpool or a funnel. Well, unfortunately, that's not what a wormhole looks like. Sorry about that. But in Star Trek Deep Space Nine, wormholes are gateways to another point in the galaxy which occur naturally. So they're not artificial, they're created naturally. They're found, and when you find them, they can become a very cheap gateway to the other sector of the galaxy. Well, what does the science say about these things? Well, wormholes were first introduced by Albert Einstein himself. Yes, it was 1935 that Einstein wrote a famous paper with his students, Nathan Rosen, called the Einstein-Rosen Bridge paper. He took two black holes, which sort of resemble a funnel, stuck them back to back. Take two funnels, cut them, stick them back to back, and if you fall into one funnel, you fall out of the other funnel. That is a wormhole. It's a gateway. It's a shortcut through space and time. Now, Einstein himself did not think that we could create a wormhole. Of course, he was playing with black holes. So it would take the energy of a black hole. But he did believe that this was very interesting because they were solutions of Einstein's equations. So think of Alice's looking glass. The looking glass of Alice is the wormhole. Alice sits in Oxford, England. On the other side is the Mad Hatter in Wonderland. And by going through the looking glass, you instantly are transported to another point in the universe. Well, you can also use this as a time machine as well. In fact, my colleague Stephen Hawking, who recently passed away, posthumously has published a book. And in the book he says, well, he's backtracking a bit. He now believes that time travel through wormholes may be possible. He used to say it was not possible, but he has since backtracked. And his latest book, written posthumously, says that perhaps wormholes can also be used as time machines. Now, what's the catch? There's always a catch someplace, otherwise somebody would have built one of these damn things years ago, right? The catch is, well, as Einstein himself realized, to create a wormhole, you need fabulous amounts of positive energy, like a black hole, and then negative energy to stabilize it, to keep it open. So it was Einstein himself who realized that positive energy, in the form of a black hole, might rip the fabric of space and time, but Stephen Hawking had a mathematical proof showing that if you have enough negative energy, you can stabilize it. Keep it stable so you can walk back and forth and not be crushed, or the wormhole wouldn't collapse on you like as it does sometimes on Star Trek. That you could keep the gateway open. So the catch is, of course, we do not have the ability to manipulate the energy of a black hole, and we can only create microscopic, minuscule quantities of negative energy in the laboratory, and so we're far, far away from being able to use the power of a wormhole. But are they possible? Yes. Do we know for sure? Well, no, because ultimately we have to rely on a higher theory to stabilize a black hole, and that theory is string theory. That's what I do for a living. That's my day job. Unfortunately, string theory is not yet advanced enough to answer all these questions. It gives us tantalizing clues that these questions are answerable, but the mathematics is horrendous. I know because I work on it. The mathematics is horrendous. At the present time, no one can conclusively say that wormholes exist and are stable. Now, some physicists have published articles saying that maybe they can be found naturally, like in Star Trek. The Big Bang inflated a tiny piece of the universe, and maybe there was a wormhole there, in which case the wormhole would have been inflated too, giving us a naturally occurring wormhole, just like in Deep Space Nine. Welcome back to Science Fantastic with Professor Michio Kaku. Yes, if you want to get on Science Fantastic and ask that question that you've always wanted to ask. Okay, let's move on now and take the next listener phone call.
Hello, my name is William. I am calling from Port Orange, Florida. I'm listening to what looks like WNDB 93.5. My question is in regards to light behaving as a wave and a particle or a particle. I've seen some videos and read some explanations about how it changes its behavior when there's observers, in other words, the observer effect. And I have also heard some explanations that when it is observed, it's really just measured, and the act of measuring does something to it that makes it behave as a particle and or wave again. So I was just wondering if it is something that science is just assuming that when they are observed that it changes its behavior, or if there is actual scientific proof that the observation messes with the experiment and collapses the wave function. Thank you very much. I love science.
Well, the answer to your questions is yes. Yes, 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 yes. Next question. Well, let me answer them one at a time now and break it down. First of all, the ancients used to wonder, what is light anyway? How fast does it move? What is it? It's such a fantastic thing, light. Well, we could actually answer all those questions now. Well, first of all, Newton thought that light was a particle. It was a particle that when it went through a prism would break up into colors, giving us the rainbow, but it was particulate. It was a particle. Then came other experiments where we showed that light waves can interfere with other light waves, and maybe that's what's happening with light. And so we began to think that light had a frequency, it had a wavelength, and it was vibrations. Then finally in the 1860s, James Clerk Maxwell, a theoretical physicist in Cambridge University, made one of the greatest insights in the history of science, which made modern technology possible. All of it because of Maxwell. However, let's take a short commercial break, and after the break, we'll try to answer the question, what the hell is light anyway? Is it a wave? Is it a particle? Is it something in between? What is it? Welcome back to Science Fantastic with Professor Michio Kaku. And before the break, we had a very important question which goes to the heart of modern physics today and why modern physics is so bizarre. Why is the quantum theory one of the weirdest theories ever proposed, and yet we need the quantum theory? Without the quantum theory, well, there's no radio, there's no television, there's no electronics. Modern technology, the transistor, the lasers, all of it depends upon the quantum theory. And it boils down to a simple question. Is light a particle or a wave? Newton thought light was a particle. Other people showed that light has wave-like properties. It has a wavelength. It has a frequency. And it's very similar to other forms of electromagnetic radiation. And the next big step was taken in the 1860s by James Clerk Maxwell. He showed that if I take an electric field and vibrate it, it creates a magnetic field. And if I take a magnet and shake a magnet, it creates an electric field. So then he asked a key question. If I vibrate an electric field to create a magnetic field, which creates an electric field to create a magnetic field, then does it propagate? Does it move all by itself? Well, he showed that it does. A wave like ripples on a pond, forms out of magnetism and electricity. And then he calculated the speed of that wave, and he was shocked. Absolutely shocked. This is one of the greatest breakthroughs in the history of Homo sapiens. He found that vibrating electric and magnetic fields that you can create in your own living room, the vibrations travel at the speed of light. And then he uttered the most important words of all time. He said, maybe this is light. And he was right. Light is an electromagnetic wave. When it vibrates even faster, it turns into ultraviolet radiation. When it vibrates slower, it turns into infrared. In fact, if you vibrate it at different frequencies, it turns into television, radio, ultraviolet, gamma rays, all all the colors, all the radiations that you hear about, can be summarized by vibrating electric and magnetic fields. The next breakthrough came with the quantum theory. And it was Einstein himself who said that light is based on photons, particles. So now we had a conflict. We had a war raging in physics, where Newton and Einstein said that light was a particle. Everyone else said, no, it's a wave. We can refract it, reflect it. It has a wavelength. We know everything about waves. So who's right? Well, actually, both are right. It was Max Born, the physicist, who finally put these two things together in a way that Einstein hated. Sorry about that, but Albert was wrong on this one. It turns out that light is a particle. It is made out of photons. Photons are particles of light. So to answer your question, is light a particle or a wave? Well, it's a particle. But the probability of finding the particle at any given point is given by a wave. So if the wave is strong at a certain point, it's likely to be there. Well, Einstein hated that idea. What? Likely? Probability? Chance? Come on, give me a break. The march of science, said Einstein, was to reduce uncertainty, to eliminate all the likelihoods of this and the likelihoods of that, to get definitive answers. So Einstein thought that the universe consisted of tiny little steel balls. These little steel balls, you knew exactly where they were. You knew their velocity, the position, no ifs, ands, or buts. That's the common sense point of view, by the way. You consciously or unconsciously think that everything is made out of definite little objects. You know exactly where they are, when they are, end of story. Well, sorry about that. That's not true. The quantum theory says that light has with it a wave, and the wave tells you where it is most likely to be found. So if the wave maximum in a certain area, then chances are that's where it is. That's called the uncertainty principle, that you don't really know where anything is at any given point, meaning that an electron, you don't really know where it is. It could be two places at the same time. Now, at this point, you may say to yourself, whoa, stop right there. Two places at the same time? Well, yes, two places at the same time. And what are the practical applications of this? Transistors, lasers, diodes, computers, iPods, the internet, all of them based upon this bizarre idea that electrons can be two places at the same time, and the probability of finding that damn electron is given by a wave. This is amazing. When I look at myself in a mirror, I realize, first of all, I'm not really looking at myself at all. I'm looking at myself, first of all, a billionth of a second ago. Let's take another short commercial break, and let's get back to Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we have one of the great paradoxes of all time. How can you be two places at the same time? Well, that's the way it is, folks. That's the way the universe operates. Now, the questioner asked, do you have to make a measurement to find out where that particle is? And yes, you have to make a measurement. And in that sense, that determines where the electron is. Now, at this point, Einstein really flipped out and said, are you saying that the process of measurement, which determines consciousness, that consciousness determining measurement determines the position of a particle? Well, Einstein hated that. What? Consciousness determining existence? Einstein thought that existence was totally independent of thought. Well, according to the Bohr interpretation, objects exist at a definite place when you make a measurement, and that requires consciousness. Now, what do modern physicists say? Most of my friends, some of them Nobel Prize winners, believe in the many worlds interpretation, and that is that the universe splits in half. The electron is one place in one universe, but the electron could be another place in another universe. The universe is constantly splitting apart And that's how you get around all the paradoxes of the quantum theory. That you don't have to have consciousness to make a measurement to determine where something is. Something is in many places because the universe splits into parallel universes. Now, if you want to know more about this, get a copy of my book, Parallel Worlds, where I talk about this. Now, does this mean that some people who have died in our universe are still alive in another universe? Well, this may freak some people out, but the answer to that is yes. In the multiverse interpretation, you can die in one universe and still live in another universe. Now, what's the catch? There's always a catch someplace. The catch is that the probability of meeting that dead person is extremely small. So small that it's not going to happen in the lifetime of the universe. So chances are, if you've died in our universe, that even if you are alive in another universe, you'll never be able to go back to the original universe you came from. Sorry about that. Okay, well, let's move on to the next listener phone call.
Hello, Professor Kaku. This is Jesse from Houston. I watch you on YouTube, watch your podcast, and listen to questions and everything. It's pretty helpful. It's very helpful, actually. I had a couple questions for you about the Parker Solar Probe. I know we're going to launch that pretty soon, a couple days, I think, a few days from now. And I understand what it does and what it's going to do and all that, but what do you think that we're going to find new particles that we've never seen before, so since we're so close to the sun, or new elements or new things that we don't know about that's going to ask more questions? And the other question was, what are we going to do with that probe? Is it going to come back to Earth, or is it going to do like a kamikaze mission like Cassini did with Cassini? Did it, are they going to do that with the Parker Solar Probe or no? Because I've never heard anything about it, so I was just seeing if you knew any more about it. And about new elements that might show up with the Parker Solar Probe.
Well, the short answer is no. We're not going to find new particles. New particles would require another large hadron collider, a $10 billion machine outside Switzerland. However, we hope to find answers to many mysteries of our sun. For example, there was a mini ice age during the medieval period. Paintings done during the Middle Ages show that certain lakes were frozen over, lakes which are not frozen over today. People are ice skating on these frozen lakes. Temperatures dropped tremendously during the certain period of the Middle Ages called the Mini Ice Age. Some people think that the variation in the sun's intensity caused that. Also, giant solar flares could wipe out communications and cause tremendous disruption on the Earth. The Carrington event of 1859, Google it, Carrington event, created so much solar activity that it wiped out telegraph transmissions on the Earth. The northern lights, usually seen at the North Pole, could be seen in Cuba. That's how powerful the radiation was from the sun. If that radiation from the Carrington event were to happen again, all hell would break loose. Property damage, $2 trillion in property damage. We'd have blackouts everywhere. Food riots would break out. Communications would go down. The internet, weather satellites, everything would go down. It would be horrible. We would be thrown back maybe 100 years into the past if another Carrington event were to happen. Could it happen again? The answer is yes. But why? I mean, how often would it happen again? It turns out that several years ago we just missed a solar flare that could have given us another Carrington event. How often are they? We don't know the answer to a lot of those questions. So we hope to find the answer by sending probes near the sun. And, well, unfortunately, many of these probes are not going to come back. Sorry about that. Okay, let's move on now to the next listener phone call.
Hi, Dr. Kaku. This is Ken. I'd like to ask about whether or not Lewis Carroll had any influence on relativity theory. As I understand it, he, in his second book of Alice, he wrote down that Alice was walking down this road that constantly changed the direction and constantly warped the path, so that when she was trying to leave a house, the road itself would change so that she would re-enter the house. The way he described it was very similar to the way relativity is described in Einstein's work. I'd like to know that, being that Lewis Carroll was a mathematician, did he have any role in the invention of relativity? Thank you.
Well, first of all, Lewis Carroll was not Lewis Carroll. He was Charles Dodgson. He wrote under a pen name because distinguished Oxford professors of mathematics are not supposed to write children's books, which then became a monster bestseller. Queen Victoria read Alice in Wonderland. Alice in Wonderland has wormholes, for example. The Looking Glass of Alice is a wormhole predicted by Einstein in 1935. But was there a direct relationship between Alice in Wonderland and Albert Einstein? To the best of our knowledge, no. We know many of the influences that influenced Einstein. One of them was a children's book. When he was a child, a children's book asked the question, what happens if you could ride alongside a telegraph wire, or ride alongside electricity in a telegraph wire? Einstein, as a 16-year-old child, changed that into a light beam, and from that got special relativity. Okay, but unfortunately, we have run out of time. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, well, this hour is your hour. That's right. You can pick up the phones and perhaps you can get on Science Fantastic. Okay, well, let's move right on now and take the first listener phone call.
Anna. 7:50 a.m. in Anchorage, Alaska. The question I had is, people keep saying that the universe is expanding, and I'm wondering what it's expanding into, since there are other universes and galaxies. Ultimately, what is the ultimate expansion? Thank you very much for the service you do and the answers you give. I find your show fascinating.
Well, let me just answer that question really simply. Our universe is expanding into another dimension. Now, think of our universe consisting of 3 dimensions, length, width, and height. If you want to locate any object in the universe, you give its length, width, and height, and bingo, you can locate any object in the universe. If you want to locate any event in the universe, you give 4 numbers: length, width, height, and time. So I live in New York. If you want to meet someone for lunch at 42nd Street and 5th Avenue on the 10th floor, you give them 3 numbers: 42nd Street on 5th Avenue on the 10th floor at noontime. And that specifies a unique event in our universe. And the thing that has puzzled physicists for centuries, in fact, is why do we live in 3 dimensions? There's nothing special about 3 or 4. You talk to a mathematician, is there anything special about 3 or 4 dimensions? And they say no. 5, 6, 7, they're all the same to a mathematician. Well, to a physicist, they're quite different, because our physical universe exists in 3 dimensions of space and 1 dimension of time. Now, the universe is expanding. We know that because of the Doppler shift. When a star, which is yellow, moves away from you, the light is stretched like an accordion, and the frequency gets lower and therefore turns reddish. When a star moves toward you, yellow light is compressed in the forward direction, and it turns slightly bluish because blue has a higher frequency and a shorter wavelength. This also works for sound. When something moves toward you, sound is high-pitched. When something moves away from you, the pitch lowers. And it sounds like this. Now, you've heard that all your life. All your life you heard that, except you never thought to ask, well, what is that? That is a Doppler shift, and that's how police give you a speeding ticket. They shine a laser beam on your license plate. The laser beam's light bounces off your license plate, goes back to the cop, and the cop then measures the Doppler shift of the reflected beam. Bingo. You have a very precise way of giving you a speeding ticket. Well, in some sense, we give a speeding ticket for stars and galaxies. And what we found was astonishing. all the galaxies, for the most part, are moving away from us. Now, some galaxies are actually moving toward us, like Andromeda, but on average, all the galaxies are moving away from us for the most part. Now, why? This means that the universe is expanding. The space between stars is expanding. And then I have to take a short commercial break. We'll answer the question, well, then what is it expanding into? And so we'll answer that after the commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question. If the universe is expanding, then what is it expanding into? Well, our universe is a bubble of some sort, so we don't know exactly the details of the bubble, but we live on the skin of the bubble, and the bubble is expanding. So take a balloon, put dots on it representing the stars and the galaxies, and the balloon is expanding. And what is it expanding into? Well, the skin, the surface of the balloon, represents the universe. And therefore, what is off the balloon? What is off the balloon is the third dimension. Now, if you're a bug living on the surface of the balloon, you can only see two dimensions, forward, backward, left, and right. Because the balloon is the universe. The balloon is everything there is. Now, where is the universe or the bubble or the balloon expanding into? It's expanding into the third dimension. Now, the bugs cannot see the third dimension. The bug's eyes can only see two dimensions, but it's expanding into the third dimension of space. Now, Einstein says our universe is a four-dimensional bubble. So what is it expanding into? The fifth dimension. Now, you can't see the fifth dimension, just like bugs cannot see off the balloon, but that's what the universe seems to be expanding into. Now, the theory which explains this is called string theory. String theory has not been verified. Now, the expanding universe theory, of course, has been verified at every time we look at the galaxies in outer space. String theory has not been verified. String theory actually predicts that the universe is expanding into 11 dimensions. Not just 4, not just 5, but 11 dimensions. And so think of a bubble bath of universes. So our universe is a bubble, and it's floating among other bubbles out there. Now, this explains, I think, a resolution between two of the great paradigms of religion. In the Christian religion, we have Genesis. In Buddhism, we have Nirvana. Now, my parents were Buddhists, and in Buddhism, there is no beginning, there is no end, there's only states of consciousness called nirvana. But I was raised as a Presbyterian as a child, and every Sunday, I went to Sunday school and learned about Genesis and the fact that the universe had a beginning, an instant, when God said, let there be light. So how can you reconcile these opposite points of view? Two totally opposite points of view. One in which there is no beginning, only states of consciousness, no beginning, no end, and the other one being a definite point when the universe began. Well, the multiverse idea coming out of string theory explains it. Because you see, our universe, our bubble, had an origin. It had a Big Bang. There was a moment when the universe came into existence. But there are other bubbles out there. And what is it expanding into? Nirvana. Something beyond the bubble. Nirvana, that is 11-dimensional hyperspace. And so string theory says basically that all the particles are nothing but vibrations on a tiny, tiny little vibrating string. That physics is the laws of harmony of the string. That chemistry is the melodies you can play on these vibrating strings. The universe is a symphony of strings. And the mind of God that Einstein wrote about in his letters and his memoirs, the mind of God would be cosmic music resonating through 11-dimensional hyperspace. So the next time you go to a planetarium and the children ask the question, if the universe is getting bigger and bigger, then what is it expanding into? You can give them the thought that, well, perhaps it's hyperspace. The universe is expanding in another dimension. Okay, well, let's move right on to the next listener phone call.
Hi, this is Kenneth. I would like to ask what your theory is on, actually my theory, that the reason why human beings and other animals don't have green fur or blue fur. I think it's probably because we're larger creatures, so that when the forest burns down or when the grass fields dry up, everything turns brown, and therefore animals and humans with like green or brown, with like brown fur would blend into like the dirt. Whereas, like other creatures that are smaller, like insects or lizards, they would be green because they could blend in with the vegetation or, like fly away or scamper to another forest. Human beings and other like mammals are larger, and so their fur would not be green because that would not be conducive to camouflage with the sky. But a butterfly, for example, that's blue and small can camouflage with the sky, whereas we cannot. So that's my theory on why, human beings do not have, like, green hair or, like, blue hair. I'd just like to know what your thoughts on that are. Thank you for your time.
Well, your theory is not too far away from evolutionary theory, which simply says that animals change generation by generation with survival for the fittest. So I think you're using that methodology, that there is a reason why certain animals have certain colors. It's because it makes their survival value higher. They can survive better to create children, to perpetuate their genes to create the next generation. So that's the basic thrust of evolution, which is also the basic thrust of your thinking. Now, of course, the precise mechanism differs from the standard theory. The standard theory would simply say that bears are brown, for example, because most of the leaves in the forest are brown. Yes, there are green leaves as well, but when you look at the habitat, the actual habitat of many of these animals, they do live in savannas. They do live in areas where there's lots of brown leaves and brown trees. Now, of course, there's bound to be exceptions to this. Lizards, for example, and reptiles could be green. But the methodology that you are mentioning is roughly the same as evolutionary theory, and that is, there's a reason. Now, that's not the only theory. Another theory simply says that's the way it is. That's the way the universe was created by God or whatever. That's how they were created, and they've been that way ever since. But if you look at the fossil record, you begin to realize that, well, we used to have dinosaurs. They don't exist anymore. In fact, if you count the fossils underneath your feet, you count them right underneath your feet right now, you begin to realize that 99.9% of those animals are now extinct. They don't walk the surface of the earth anymore. And so, going backwards in time, we see a continual change, that animals do change generation by generation. And the mechanism for change is that you have a higher survival value, which is, of course, where you're coming from, that animals have a certain color for a reason. It's not because they were simply created that way, or magic, or whatever. It's because it increases their survival, and so they can survive to propagate their genes. Now, the precise mechanism differs, of course, from the standard theory, but I think you're leading in that direction, and that is, there is a rhyme or reason to the reason why Mother Nature is the way it is, and it's because of survival of the fittest. Okay, well, let's move on to the next listener phone call.
Hello, my name is Patrick. I'm listening to 7:50 a.m. in Palmer, Alaska, and I had a question about a book I read. It's called Red Theory, I believe, about black holes. And in the book it said if a human gets sucked into a black hole and someone is watching, the person watching will see the other person die instantly, but to the person who was sucked into the black hole, it will be an eternity of stretching and pain, and they will be alive for the whole thing. I was wondering how that would work.
Yeah, you were talking about the fact that if you fall into a black hole, God forbid, right? It's a horrible experience. But if you were to, you would get vast distortions of time. Now, you got it backwards. it turns out that you falling into a black hole would fall into a black hole in your time almost instantly. So as you approach the black hole, you see the thing coming at you really fast, and then whoop, you're dead. But from someone from the outside, way outside with a telescope, looking at you from the outside, you are almost frozen, almost paralyzed, and you fall into the black hole extremely slowly. And in fact, mathematically, it takes an infinite amount of time to actually fall into the black hole. So there was even a science fiction story once where the bad guy falls into a black hole and he screams for 1,000 years. Well, we'll answer that question after the break about Einstein's theory of black holes. Fantastic with Professor Michio Kaku. Well, we had a call coming in before the break. What happens when you fall into a black hole? How is it possible that you, as you fall into a black hole, you die almost instantly, but someone from the outside, far away, looking at you with a telescope, would see that you are frozen in time, paralyzed, and it takes thousands of years for you to fall into a black hole? How does that work? Well, first of all, falling into a black hole is not very pleasant. Many bad things happen to you. Among them, spaghettification. It turns out that your feet are attracted to the black hole a little bit faster than your head, and so you're stretched as a consequence by tidal forces, and you look like a noodle. We call it spaghettification. And so one of the horrible facts about you falling into a black hole is you become a noodle of spaghetti as you get into a black hole. As you get even closer to the event horizon of a black hole, even the noodle begins to fall apart, and the atoms, the very atoms of your body, become noodles, and they get ripped apart, and you basically turn into cosmic dust and spaghetti as you fall into a black hole. Not very pleasant. Well, the way Einstein looked at it is that time beats at different rates at different points in the universe. So think of putting a clock at every point in your room. Okay? So every point in your room, there's a clock. Thousands of clocks right in your room. Einstein says that they don't necessarily beat at the same rate. Some clocks can beat faster than other clocks. For example, on the moon, a clock on the moon beats faster than a clock on the Earth. A clock on Jupiter beats slower than a clock on the Earth. And all these things are measurable. This is not science fiction. This is not speculation. We measure these things in the laboratory. And so the man falling into a black hole has a clock. His clock is different from a clock on the outside. For the man falling into the black hole, his clock says he dies almost instantly. Now, a clock from the outside gets light from the man falling into the black hole, but that light is affected by gravity. Gravity pulls on that light beam, stretching it, so it turns out that you get what is called a redshift, and things start to slow down in that light beam. So a light beam shot from a man who is falling into a black hole, that light beam is stretched, called the redshift, and time is also slowed down because of gravity. So the gravity is so intense of a black hole that it slows down time, stretches the light beam, and so you looking at the man falling into a black hole, you see that he becomes reddish, he becomes like spaghetti, and he's basically paralyzed. And again, not a very pleasant thing to happen. Now, we've never observed this, of course, because, of course, the nearest black hole that we study regularly is at the center of the galaxy, and that black hole is, something like 50,000 light years from the Earth. And so we've never done this experiment. But on theory, so far, this is what the theory predicts, and so far we have no violations of Einstein's theory of gravity. Let me repeat that again. We have no violations at all of Einstein's theory of gravity. Every time it comes out right on the dot as Einstein predicted 100 years ago. Science Fantastic with Professor Michio Kaku. Give us a call and maybe you can get on national radio. Okay, let's move on now to the next listener phone call.
Hello, Professor Kaku. My name is Jay. I listen on WNDB in Daytona Beach, Florida. And I love your show. Thank you. If an object weighed at the North Pole and then taken to the Earth's equator and weighed again, would the same object weigh the same? Would the object weigh less at the equator than at either pole? The object would be rotating at the equator at the rate of 1,000 miles per hour. Would the centrifugal force cause the object to weigh less at the equator than at either of the poles? I would appreciate the answer to this, and thank you very much. You have a good day.
Okay, well, the answer to your question is yes, you weigh less on the equator than on the North Pole. And even Isaac Newton could have calculated that. First of all, you're right. On the equator, you're traveling at about 1,000 miles per hour. You are traveling around the circumference of the Earth, which is 24,000 miles. And there are 24 hours in a day. You divide, bingo, you get the fact you're traveling at 1,000 miles per hour on the equator. Now, you can also calculate the centrifugal force. The centrifugal force is mass times the velocity squared divided by the radius of the Earth. So, bingo, you just plug it into the equation, and you can calculate the centrifugal force by when you're sitting on the equator. Now, when you're sitting on the North Pole, there's no centrifugal force. You're just feeling the force of gravity, which is mass, the two masses, times the gravitational constant divided by the radius squared. So you compare the two numbers, which you can do in a simple calculator, and bingo, you get the fact that you are you weigh slightly less on the equator than on the North Pole because of the centrifugal force. You're absolutely right. Okay, well, let's move on now to the next listener phone call.
Hello, this is Armand from Queens, and I listen to on YouTube. I saw an article that said, from Big Think, which is kind of like, a science article, science like publication. It said, mice can live forever. Soon you'll be able to also. What do you think about that? That sounds awesome, right? Do you think it's possible that we can live forever? And it's coming faster than I even thought. I thought it was like 2020. Guess it's coming even sooner. Thank you very much.
Well, I don't think we can live forever by 2020, but I think there are two avenues that are very promising. First is biological or genetic immortality, and the second is digital immortality, both of which are mentioned in my book, The Future of Humanity. So let me explain. First of all, we know more or less what aging is. We didn't know what aging was for centuries, but now we have a real rough picture of what aging is. Aging is the buildup of errors in your cells, genetic errors, chemical errors. Errors build up every time cells divide, for example. Now, there's something called entropy, which is the second law of thermodynamics, which says that everything gets old, everything rusts, everything corrodes, everything eventually dies. But there is a loophole to that, and that is if you add outside energy from, let's say, the sun, or outside information from genetics, you can slow down that process and even perhaps reverse it. And so, by genetic engineering, we may be able to cure the errors in our genes and perhaps live forever. Now, how would we do that? First of all, think of a car. Where does aging take place in a car? Well, aging takes place in the engine. Where does aging take place in our bodies? Well, we'll answer that after the break. Let's take a short commercial break, and after the break, we're going to answer the question, how do you live forever? to Science Fantastic with Professor Michio Kaku. And before the break, we had a question. Is it possible to become immortal? And why should we want to do that? And what are the consequences? Well, first of all, the answer is yes. There's nothing in the laws of physics preventing us from becoming immortal, but you have to add energy and information from the outside in order to conform with the laws of physics. So take a look at a car. Where does aging take place in a car? Well, the engine. Why the engine? That's where you have moving parts and you have combustion. Well, what is the engine of a cell? The engine of a cell is the mitochondria. So where does most of aging take place? Air buildup in a cell. The mitochondria. Bingo. So in the future, we'll be able to sequence all the errors that build up in the mitochondria and elsewhere and use genetic engineering to reverse the damage. So in principle, it might be possible to extend the human lifespan. Another way is to take the genome of thousands, millions of old people, compare that with the genome of thousands, millions of young people, and subtract in a computer. Find out where the air buildup takes place, because that's what aging is, the buildup of mistakes inside our DNA. That's why cells become sluggish, and eventually they die. In fact, that's why we die. And take a look at animals. The Greenland shark can live to be almost 500 years old. This is not superstition. We know that because the eyeball of the Greenland shark adds a layer every year. So by simply counting the layers, like counting the tree rings, you can, bingo, calculate the age of a Greenland shark. And they live almost 500 years. Think about that. And also elephants. Did you know that elephants almost rarely get cancer? Now, sharks do get cancer. There was a fad a few years ago that sharks don't get cancer. Wrong. But elephants, they rarely get cancer. And they're big. Lots of places to get cancer. Why? Because of the gene P53. It turns out that healthy P53s help to counteract cancer. We have, I think, 2 copies. Elephants have something like almost 20 copies of P53. And because of that, they have error correction mechanisms, and they don't get cancer. Now, the second way to become immortal is digital immortality, and that is to digitize everything known about you and eventually digitize your brain. Digitize your credit card transaction, Instagram photographs, biographies, videotapes, everything, including every single neuron inside your brain. That's called the Connectome Project. And from that, you can build a reasonable copy of you. For example, as a hologram that you can talk to, the image would be a near representation of who you are. And every year, it would get closer and closer to the real you. Now, of course, it's not really the you, the biological you. It is a copy of you. But when you die, your personality does not necessarily have to die with you. Now, during the Middle Ages, we had something called dualism. That is, you had the soul on one hand and the body on the other hand, and they were separate. Then came, in the 20th century, neuroscience. We said, bah, humbug. There's no soul. It's just neurons. That's all it is up there in our brain, neurons. Well, now we're coming full circle. Now we're going back to the Middle Ages, because we now realize that the so-called soul might be able to be represented by information, by digitizing everything known about you. So in the library, for example, you'll take out a book, not about Winston Churchill, but you'll talk to Winston Churchill. All his mannerisms, speeches, thinking patterns are all codified, and I would love the opportunity to talk to Einstein. Think about that for a moment. Talking to historical figures that have been digitized, and one day you might be digitized as well. You might live forever someplace, and you'll be able to have a conversation with your great-great-great-great-great-great-grandkids and give them advice. Advice even though your mortal body has long since disappeared. Now, the point is that all of this is consistent with the laws of physics. I have violated no law of physics in mentioning the fact that, yes, at some point in the future, digital and biological immortality may become realized. And then the key question is when? Well, digital immortality is coming pretty fast. Already there's Silicon Valley companies offering a digital version of what is known about you today. In the future, it'll become extremely accurate. And once we sequence the brain, the Connectome Project may be able to give us a copy of the brain. But biological immortality? Decades away. That doesn't mean it's impossible, but I think given the rate at which we're understanding genetics, it's still decades away. As someone once told me, our generation, the generation now alive, may be the last generation to die. In other words, our grandkids may have the option of hitting the age of 30 and then stopping and just living forever. Well, if you want to know more about the aging process and how it's going to be very important for us in the future, get a copy of my book, The Future of Humanity. And in my book, I mentioned that we're not necessarily going to overpopulate the earth as we begin to live forever. Look at Japan. Japan has the oldest living ethnic group on the earth, Japanese women. They hold the world's record. And the Japanese population is collapsing. When people live longer, they have fewer children. And that's the reason why Japan now and Europe in the future will gradually get smaller and smaller. Well, unfortunately, that's it for Science Fantastic.